Hi, and welcome back. This is actually going to be the final part of Kuchemann's book, really because kind of in chapter 6, 7, 8, and then some conclusions in chapter 9, he really goes into, I'd say, a ton of detail. So, as a reader, go through it. I'm going to hit the high level of way tops because what you're really finding there is sort of, at the time Kuchemann had this book together, it was sort of bleeding edge. So it was almost kind of covering the latest research, things they were struggling through. Um, there's, I'd say if you're designing supersonic aircraft, this is kind of where you would need to go hit up some other literature that's a little bit more complete that would show up. So I'll just kind of do some highlights and in kind of three different sections. And so the first section in chapter 6, the first one of note is there's a little bit here where Kuhlmann kind of drives and looks at some equations and say, hey, this is why there's a good reason for model to be L over D is 3 times Mach number plus 3 over Mach number. And then he also showed that there's the propulsive coefficient kind of went Mach over Mach point plus 3. And so, and throughout his book, this is where he's saying, oftentimes we have in the Bernoulli range equation, we have instead of H, eta, L over D, and he just said this combination is 3. Well, that's why. And it's not 3. We've actually had it go more than 3 based on some advances in the last couple of decades. But this is where he sort of shows that coming in. Okay. The other piece that in chapter 6, this is really all about kind of slender supersonic aircraft. He really does a good job of sort of showing the challenge that ultimately the thing that you really have to solve for, the biggest problem, and this is plotted as lift coefficient versus L over D. And you're going to have something like this, and this would be, stall, but this is at your cruise condition. Okay, so there's cruise. But then in order to honestly operate out of an airfield, given runway length and things like that, you needed something more along the lines of this airfield. And so, in fact, you needed like this dot on CL for airfield. And so really the biggest challenge, as he's sort of framing it, is this one right here, which is how do you design an aircraft that can fly like this out of an airfield, but then cruise like that. And ultimately that's where, kind of the slender delta wing aircraft comes from, okay? Now, there are reasons for having wing sweep. One of them is during the sort of the drag wall at Mach 1, you take that sort of that big drag and you end up shifting it, to the right, which is helpful, and you lower it. So for a jet engine that's, trying to cross, it might not be able to cross that one given the size of a jet engine, but it can certainly cross that drag peak. And that's why what's one of the reasons you would do wing sweep. The second one is actually this airfield thing, because what's going to happen, and Kuchemann does a really good job in chapter 6 kind of covering why, is you actually get a vortex, strong vortex coming off of this at high angles of attack at that airfield. And so, yes, it's pretty draggy, but it actually lets you hit these sort of high lift coefficients in that airfield. And so really there's kind of two reasons for sweep. This one particularly is if you're constrained through all the rest of your features of your engine, your takeoff roll, all those different things, that this is a high reason why you have high-speed aircraft have wing sweeps. Now, it may not be true in different situations. It really depends on your engine sizing and noise regulations and things like that. But this is sort of what he was saying. And then probably the most interesting part of chapter 6 is he has a really sort of deep dive into some of the problems then of aircraft of this kind of shape. And the biggest one is actually this Dutch roll. But the final diagram that really kind of blows my mind is this one. See if I can draw it well. And it was angle of attack versus sort of the span of lift, and as you're sort of designing the aircraft. And basically, like, here was the limit for cabin angle. And for reference, it was something like 15 degrees. And after that, it was just like, whoa, this is too much of an angle. And then there was Dutch roll was sort of this way. And then like this was sort of a vortex breakdown. And I think this was cruise, the cruise condition, that was okay. And then this final piece was lift at low speeds. And so what it does, and you can see here, it basically said like, here is your super narrow range of operation. Beyond that, you'd either be unstable, or the cabin angle would be too much, or your vortex would break down, or you wouldn't be good at cruise. So anyways, it's really sort of interesting to show kind of as they were working through, and again, lots of good physics and experimentation and results that you see there under chapter 6, under kind of that slender wing. Now it is worth, you should go Google the Kuchemann tau method, because you actually put together a lot more things beyond kind of that what we just showed here in this book. So there's good papers out there if you search Kuchemann tau method that sort of builds upon all of this stuff. Okay, chapter 7, I'll do it here. It's sort of a short read, but it's basically short haul, and we don't often think about short haul. Maybe you're military designing aircraft and you just need just kind of short ranges. But it was sort of this interesting characteristic that normally, and I'll try to draw this in two colors. If this is lift over drag, and again lift coefficient, that this might be your classical design, and that what you could be very interested in having though is a design that does this, and so that you can achieve this at an airfield. Right, so your drag didn't completely, you didn't fully separate your wings, and so you might be able to do that in an airfield. And let's say this was your cruise condition classically. Well, yeah, you can certainly match that cruise condition L over D classically as well too. And so super interesting. Just goes to show that for the most part, most of this book has been about designing, long-haul aircraft, and ultimately with this idea towards high-speed aircraft, where really the markets you're looking for is transoceanic and things like that. It's an interesting, good chapter here on just, hey, if that's not what you're looking for, if you're truly trying to build something that can go 500 miles or 1,000 miles, there actually is some pretty interesting characteristics here you can do with short haul. In fact, we're starting to see that there's a little bit of a new market here for sort of these short takeoff vehicles. Sometimes you're seeing it in terms of drones, like drones that can take off in like 20 feet and not have to be a quad rotor, but it's kind of a fixed wing, but they can get off the ground in 20 feet and go forward. So this is almost coming back in some interesting design cases. Right? And then chapter 8, this is fascinating, and this is all about waveriders. And he does a pretty complete job of talking through the waverider, if this is the first time you've seen it. But ultimately, a waverider, and I'll try to draw sort of the simple carrot version. Imagine I'm flying an inverted carrot like that. It's not a great vehicle. But as you fly faster and faster, the shock is getting closer and closer to the vehicle. At some point, it's actually worth sort of having your vehicle reach out, if you will, and touch it from a design point of view, such that the shock is fully attached, right? And when the shock is fully attached, and the shock might be doing something different below here, when it's fully attached, you get a high pressure region below that the air can't escape around. So you get this increased lift. And so there's all sorts of methods, and really, the Kuchemann book was sort of written in 78. There's a whole bunch of research and a bunch of things that have kind of happened since that time. So if this is of interest, Kuchemann is a good start of it, but certainly you should go kind of dive into the literature. But what I haven't seen anywhere else is really the diagram there in Kuchemann chapter 8 that sort of puts it all together in sort of the most practical way possible. And certainly aircraft design is a very multidisciplinary option, but this diagram almost makes this entire book worth it, right? And I'll try to sort of recreate it for the most part here, although inaccurately. So on the bottom here, this will be Mach number. And then, I forget, I think this is like, I didn't write down the axis. This is somehow lift. You better look at the book. I forget the actual axis, but I know the punchline. That basically below here, this is no go. This is, you don't have enough runway length effectively to take off. So anything below this line, you don't have enough lift. I think this is sea lift. And then here's the Mach number, so you do this. And then there's some really interesting, the lines, the contour lines themselves are actually contour lines of distance, how far they can go around the globe. And so you sort of have these lines of, for your subsonic aircraft. And then you get into this regime, and I'm going to draw this line first, like that. You get into this regime here, where this is actually Slender aircraft, which is this sort of thing over here. Right, no longer do you do your sort of standard like Boeing or Airbus kind of standard vehicle you're seeing. You would switch to something looking more like this, more like the Concorde. And this line here is sort of where all of a sudden what the waveriders come in. And this line is beta S over L equals 1, which is the mathematical equivalent of this, which is the shock is the shock is touching the side of the vehicle. And so really there's this sort of interesting curve where being a waverider should theoretically be worth it. Now, the challenges on waverider, and I'll kind of use that just to sort of finish the video. The challenges of waverider is actually the volume here inside of this. That it gets pretty challenging because you do actually want to carry a payload. So you're challenged with volume, and then this gets really, really thin going forward. So in fact, here at Venus, we looked into the waveriders for a little bit. We're no longer doing waverider because we're actually focusing in on Mach 4, and that's a little bit too slow for waverider action. But back when we were looking at higher speeds as a boost glide vehicle, we certainly took a dive into the waveriders. And what I can tell you is volume is challenging, and then because it gets thinner up front, your center of gravity gets challenging. It get too far back. In fact, you almost end up having to put so much ballast up front that your payload becomes challenging. So certainly some interesting technologies. So if waverider is of interest to you, and then this is a high area of research, so there's tons of research papers out there right now on waveriders, on waverider design, how you incorporate this into working vehicles with engines and things like that. And then Kuchemann does talk about sort of propulsion integration, because once you get up to these really high speeds, that's really what it kind of becomes about, is can you take your system and sort of compress, if this is your vehicle, can you take it and have all of this compression of the air, and then can you have all your combustion sort of happen at once? That way your combustion is doing this, kind of using this as a nozzle of your combustion. So he talks through that a little bit too. So Kuchemann's, it's really this great book. The last couple of chapters are pretty deep and heavy. This really is the way tops. He does a lot of sort of explaining and kind of talking through some of the more, as he wrote it, some of the most recent research. So you'll see some of the data behind, say, the curling vortex coming around here, or you'll see some of the data behind the waverider, some of the things talking about like the viscous changes to this if you have to do that. A little bit into the heating, right? Once you get up to these speeds, there is quite a bit of challenge with heating, and so read through it. And then this is this book in its entirety was really just a tremendous book. And again, I'll sort of finish by saying what's most appreciated about this book is how much you can do with the analysis, where you get really deep into the analysis and a way to truly examine the pros and cons of vehicle design and configuration at the system level. And so we sort of get trapped. If you're just trying to make a subsonic aircraft better, your design space really isn't that big. You're only just kind of pushing on a few little boundaries. But if you're truly trying to make a whole new class, say a supersonic or a short haul or waverider, it's a whole new class, and you really appreciate Kuchemann for having sort of that whole systematic view, solving things at the systems level, and then also kind of digging through that rigorous analysis, because even today with all the computers we have, nothing beats truly having that sort of analysis first, things you can program it. And honestly, it's things that, as a designer, on your laptop, you can crank through a whole bunch of designs and even some optimizations now, given today's programming, based on this analysis. Right? Kuchemann was doing this analysis just to try and, have some graphs like this to guide some stuff. But now the power today is now all of those tools and analysis you can do as one designer on one laptop. And so really, really powerful book. So I hope you've enjoyed this first season of Book Club, and we'll see you on the next one.